Thank you very much, everybody, for joining us. It is a great pleasure to have with us today for our weekly astrophysics seminar, Michalis Agathos from Cambridge. Michalis did his undergraduate degree at the National Technical University in Athens, and his graduate studies, his master's degree in Utrecht in the Netherlands, and then he got his PhD from the University of Amsterdam. For his postdoctoral work, he moved first to Cambridge and then to TPI Jena in Germany. And then since 2019, he's back in Cambridge and has been a member of the LIGO-Virgo collaboration since 2011. So he will talk to us today about testing general relativity with gravitational wave detections. We're very happy to have you here. Michali, without further ado, the floor is yours.
Thank you very much, Vasiliki, for the introduction, and thank you, of course, for the kind invitation, and thanks to everyone also for attending. So, right. So I was just saying to Vasiliki that I had a rough night yesterday, so I will do my best. I'll do my best to not be the first person to sleep through their own talk. So yeah, but let's see how it goes. And I hope everyone is doing well in these difficult times. I know this is really, unlikely for everyone, but still, this is my hope. And so let's get going because we have plenty of things to cover. I think I will stop my video streaming now because we don't want to lose bandwidth, and my connection can be kind of patchy at times. So I will stop my video if that's okay. So yes, so I actually a couple of weeks ago I attended a few weeks ago I attended one of your seminars with Manos Zapartas, and I remember that he had a very a very impressive cover slide with a dragon or so. So I thought I would top it up. I thought I would go over the top. So in my cover slide you will see not one but two dragons, with their entire families and in-laws, so 17 in total, and three unicorns, one with an eye patch. You also see I've also drawn very in great detail like the entire Smurf village and an Earth a planet as tricycle. So it's kind of thing that when you were a kid, you would imagine what infinity looks like, and you would see outside in the night sky, and you would think what you would encounter if the universe indeed goes on forever and ever until infinity. And for some reason, the object that I always thought about was a giant tricycle. So so it's kind of over the top, but unfortunately these all fell into these two black holes, so you cannot see any of those. The black holes themselves, I didn't draw them. I stole them from a colleague, as you can see. But everything else, that was me. So, so the unfortunate thing is that the black holes are enormous sinks of information. So you cannot get much information out of them, other than a couple of numbers like the mass and the spin. So very simple objects in GR, and we will see how this simplicity can help us perform tests of general relativity with the gravitational wave signal that comes to us from the merger of black hole binaries. So I'm trying to, okay, I hope you see the next slide. So this is the outline of my talk. So first I will go through some motivation, if it's at all necessary even. And then I will take you through some results on tests of GR with gravitational waves from the first detection, GW150914, to the entire most recently published catalog of detections of black hole binaries, of compact binary coalescences, which we call GW Gravitational Wave Transient Catalog number 2, which includes about 50 sources, 50 events. So then I will kind of categorize the tests of GR that we can perform with gravitational waves from the systems, from coalescing black holes and neutron star binaries, into different categories. So that have to do with different stages of the life of a gravitational wave and the nature of compact objects. And then I will just briefly mention some future prospects if there is time before my conclusions. So for people who are not really familiar with the details of gravitational wave theory, I have just one slide. So hop onto the Gravitational Wave Theory Express and try to just take out whatever you can out of it if you're not familiar with the theory. So on the top, you can see Einstein's equations, the Einstein tensor on the left, the stress energy tensor on the right for matter. And on the top right, you can see how we can split the metric into a background part, which for simplicity, you can take it to be the Minkowski metric, plus a small perturbation. So this small perturbation helps us to kind of simplify the equations of Einstein's general relativity by linearizing them. So you can see, we can construct the linearized Einstein tensor to leading order. And then if we choose the correct gauge, we can simplify this equation to give us something that looks like a wave equation for H, or for some kind of transformation of H. So the perturbation follows a wave equation. And if we, in vacuum, so, when this wave propagates through vacuum space, the right-hand side will be 0. It is sourced by matter, of course. But when the, in vacuum, it would basically be a wave that propagates at the speed of light. So then you can kind of, at leading order, you can come up with a simple calculation that gives you what sources these gravitational waves, and you can see that at leading order, the source is an accelerating quadrupole, mass quadrupole. If you have a non-axisymmetric mass distribution that kind of performs accelerated motion, that will feed gravitational waves. So, gravitational wave sources of interest of cosmological or astrophysical origin would be things like at large scales would be huge asymmetric mass distribution that accelerate very rapidly. So a typical ideal system would be a compact binary system where you would have, for example, 2 black holes orbiting each other and losing energy in gravitational waves and eventually merging with each other. Other events of interest would be supernova explosions, of course, or cosmic scale things like cosmic string networks or phase transition in the early universe, which would lead to kind of bubble nucleation and emission of a gravitational wave stochastic background, or other violent similar processes in the early universe or in astrophysics. And these are the really nice instruments that led gravitational wave science basically from 0 to hero in the last 5 years. So just a reminder that before 2015, we didn't even have a single gravitational wave detection. Now we have claimed 50 already. Something happened, I think. Are you still with me?
We're still with you. We can hear you, but
I think my screen sharing has kind of
hold on.
stopped.
Hold on.
Katerina has started screen sharing.
Yes, please screen share again, Michalis.
Okay. Okay, I think this works. By the way, if you have any questions while I'm talking, please interrupt, and make it. Let's make this interactive. I really, enjoy people just jumping in and asking questions. So we have 2 LIGO detectors in the US, one in Livingston, Louisiana, and one in Hanford, Washington, and 1 Virgo detector in Cascina, close to Pisa in Italy. And these 3 instruments have been observing since 2015 or 2017 for Virgo, and they have detected all the gravitational waves that we have, that I will be talking about. And we recently had the addition of CAGRA, not at design sensitivity yet, so it needs some upgrades to be competitive with the other three, but they are really progressing very fast. And it will be a cryogenic detector, the first cryogenic detector. And we also have plans for a third LIGO detector in India after 2022. So in total, we will have soon a network of 5 ground-based interferometers. And this is the general plan for observations. So we call those observing runs. So O1 started in 2015 after a major upgrade in the LIGO and Virgo detectors. That lasted for a few months. Then O2 in 2016, 2017, when Virgo also joined in for the last bit. And when we observed the first gravitational wave from a neutron star binary. Then O3 has just finished a few months ago. We had CAGRA joining at the second half. And then, so until the first half of O3, we have observed quite a lot and published results about quite a lot of gravitational wave events, mostly from binary black hole coalescences. And then we hope with increased sensitivity, so you can see, the increased sensitivity, you can see it projected as the reach of each detector, of each observing run, at each observing run for a typical neutron star binary. So, when you see 80 megaparsecs or 105 to 130 megaparsecs, it's the estimated range of the detector to be able to observe, the horizon within which the detector can observe a typical neutron star binary coalescence. So, as we improve the sensitivity of our detector, we suppress the noise, the detector become sensitive to further and further distances, to smaller and smaller amplitudes, gravitational wave amplitudes. So eventually, the rate, since we have access to larger parts of the universe, larger volumes, the rate at which we will be observing gravitational wave events will increase dramatically, because the gravitational wave amplitude goes as 1 over r, where r is the distance to the source, and if you increase the sensitivity by let's say a factor of 2, you will get a factor of 8 more universe accessible to you. So, the rate gets multiplied by 8. So already in O1, we saw the first gravitational wave detection together with another 3 pairs of black hole binaries that merged into a larger black hole. That was O1. In O2, we saw first neutron star binary coalescence that you can see at the bottom, and a few more black hole binaries. So in total 10 black hole binaries and 1 neutron star binary. This made up the first catalog of gravitational wave transit events, the GWTC1. And look at this, within 1 year, we just ramped up the sensitivity and got all these nice. So in these plots, you will see the LIGO Virgo detected black hole binaries in blue. The purple points are the electromagnetic black holes, and the yellow ones are the electromagnetically observed neutron stars in our galaxy. And the orange neutron stars are the ones detected by LIGO and Virgo. So, you can see how the number of black holes has proliferated throughout the last 5 years quite rapidly. And, if I want to be a bit mean towards my electromagnetic telescope colleagues, I would say I don't see such an increase in the number of purple points. So come on, guys, you need to up your game a little bit. But yeah, it's good that we start seeing a new population of black holes, and you can see that it's different than the population we've seen electromagnetically in terms of mass. So in the y-axis, you will see the mass, and the distribution of masses seems to be quite different than what we see with electromagnetic telescopes. So we have plenty of black hole binaries, and one may say, we may want to try to test those to use them to test general relativity. And okay, that's kind of obvious to me and to people who are familiar with GR and astrophysics, but maybe some motivation is needed for people who are not familiar. So first of all, you know, it's kind of obvious that black holes are, first of all, you know, what's the most interesting thing predicted by general relativity, the most interesting object, astrophysical object predicted by GR, and I would say it's a black hole, since, you know, it's a really simple object. It's basically made of pure vacuum, so it's extremely simple. It's extremely useful to test the dynamics of space-time itself. So when you have, so you know, what's even better than just one black hole? It's basically two black holes that collide each other at close to the speed of light. So you get a piece of space-time that is really strongly wrapped and curved and dynamical. And that's an ideal scenario to test the dynamics of general relativity, so the geometry dynamics of GR. And, you know, one would say, well, GR has been tested extensively throughout the last century. So, you know, all these different plots, they are taken by a living review article by Clifford Will. And these show the great extent to which people have tested different fundamental principles of GR, like the equivalence, the weak equivalence principle, Lorentz invariance, etc. And you can see, you know, to a great, or to 1 part in 10 to the minus 12 or 10 to the minus 1 part in 10 to the 20 or 21. That's quite impressive. However, you know, all these tests, and here you can see why neutron star and black hole binaries are different. So you can see that all these tests are performed mainly in in the weak field slash slowly moving, so non-relativistic regime. And you can see this in these kind of plots where you, on the y-axis you have curvature, a scale for curvature, and on the x-axis you have the gravitational wave, well, the strength of the gravitational wave field, of the gravitational field, more or less. So you can see the different kind of astrophysical systems populating this this plane, and black hole binaries and neutron star binaries are all the way up here. So we're dealing with really relativistic strong field sources. So the same here. So even pulsar timing arrays, sorry, even binary pulsars, which are considered to be so far the most relativistic astrophysical system that we can measure very accurately, they are a few orders of magnitude away from the very strong relativistic regime. So again, here you have the Hastello binary pulsar with a famous plot that kind of indirectly gave the evidence for the emission of gravitational radiation from that binary. So you have on the plot on the top right, you have the orbital decay, more or less. So, you know, the fact that the periastron time is shifted in this way, this parabolic way, more or less, gives indications that the system loses energy. And if you plot the prediction of GR, of gravitational wave emission in GR, then you can show that, you know, these points are together with their error bars, they just, you know, the error bars are just too small to be visible. And the prediction from GR for the orbital decay due to gravitational wave emission is right, you know, right spot on. It's a great demonstration of the accuracy of this observation, and that won the Nobel Prize in 1993. But even so, the most relativistic binary pulsars that we have been observed have are relatively non-relativistic. So the orbital velocities of the order of 10 to minus 3, and the gravitational wave in the gravitational field strength is, or the compactness, as we call it, is of the order 10 to minus 6. So there are a few more orders of magnitude to cover. And if you think about coalescing binaries, black hole binaries, these are basically reaching curvatures or compactness of order 1. So when the two black holes merge together, they reach maximal compactness because they eventually form a new black hole of compactness 0.5. And towards the merger, when they plunge into each other, they reach relativistic velocities of the order of 40% of the speed of light or more. So yeah, and the other famous plot that you can see on the bottom right is a number of measurements of different post-Keplerian parameters from the double binary from the double pulsar, plotted as bands on the parameter space of the binary. So the mass 1, mass 2 plane. And so these are one-dimensional bands because you have like a one parameter measurement. And you can see how this independent measurements of the different post-Keplerian parameters, they all pass through a very small region over here, which shows consistency with the predictions of the theory. So, this is still, it's a really impressive result, but it's still not in the most relativistic regime that we can think of. On the other hand, you have, for example, for the first gravitational wave detection, the source, the black hole binary that sourced this event, it was made of two black holes of roughly 30 solar masses each, and some facts that show the nature of this merger. Of course, the compactness reached 1/2 towards merger as the two black holes merged into one. The gravitational wave frequency very rapidly, dynamically evolved from about 30 hertz at the time when the signal came into the LIGO Virgo sensitivity band. It went up to 132 hertz during plunge and 250 hertz when the final black hole kind of radiated away the residual asymmetries. And this whole dynamical process happened within 0.2 seconds. So that's quite a, for such an astrophysical object, that's really an impressive dynamical effect. In the same way, you can have a look at the orbital velocity, which evolved from about 3% of the speed of light to 13% of the speed of light towards the end of the INSPIRAL, and about half the speed of light towards merger. And you can also have see how the orbital period decayed very dynamically, and the energy that was radiating gravitational waves in these 0.2 seconds was an impressive 3 solar masses. Turned into pure gravitational wave radiation within 0.2 seconds. That's a huge power output. So we're definitely dealing with a strong field source, and it's obviously a highly relativistic system. Another motivation for testing GR with gravitational waves comes from theoretical considerations. So this table is kind of stolen from an old paper but now it's old because of what happened since 2015. But it was an extensive review by Bert and many other authors, and this was the state of the field, of the theoretical field at the moment. Some things have changed in this table, so that there are plenty of candidates of contenders for being the underlying theory of gravity that that are trying to compete with GR. And it would be nice to have experimental evidence for either favoring or disfavoring each theory over general relativity. And each of these theories motivated, some of them by considerations, theoretical considerations like UV completion of GR, or astrophysical considerations like replacing the need for dark matter, for example, or dark energy. So you can see, many of these theories are even well posed, which is a difficult thing to show. And they all give modified gravitational wave signals for compact binaries. So let's now have a look at the problem itself. So what we want to go through in this talk is the way in which we can use the theory and the data to perform tests of general relativity. So this problem comes in two phases, in two stages, let's say. So first we have the direct problem of basically source modeling, which states that, given a gravitational wave source of these properties, of known properties, what is the gravitational wave signal that will that will come out of this system, the exact waveform that will come out. And this already is a very difficult problem to solve to begin with. So yeah, in this animation, in this video, you can see like the standard black hole binary coalescence towards the end of the INSPIRAL and the merger. So the thing that you see at the bottom of the animation is the gravitational waveform that gets produced by this, and that will be observed by our detectors. And it's really non-trivial to derive this analytically or numerically. Once you have a model for your black hole binaries, and you have sufficiently covered the parameter space, like different masses, different spins of the black holes, different orientations with respect to the line of sight, then you need to deal with the inverse problem, which has to do with data analysis, which basically is asking, given a set of noisy data, and assuming that you have a gravitational wave signal in this data, what are the properties of the source that emitted that signal? So, and then you run your you set up your Markov chain Monte Carlo analysis or nested sampling, and you basically try to cover the parameter space, produce waveform signals based on your model, and then try to match them against the observed data. And in the end, you end up with probabilistic distributions, what we call the posteriors, which give you the measurements of your parameters. So you have like one-dimensional posteriors like this on mass 1 or mass 2 of the binary. You can plot a joint posterior in 2 dimensions, or a sky location, a sky map for the location of the source in the sky, which will help you kind of identify the source by also pointing telescopes towards it. So all these is very useful for astrophysics and so on, but we want to use it for testing GR, of course. So let's go very briefly into source modeling. So the two-body problem in GR is non-analytically solvable, but there are good approximations to it. And post-Newtonian expansion of the orbital dynamics is a way to go. And it will give you, for quasi-circular inspirals, because we assume these binaries to be relatively old and have circularized over millions and millions of years. So we assume quasi-circular inspirals and a simple frequency domain model for the waveform looks like this. So you have the gravitational wave strain. So the signal that ends up in your detector output being made of an amplitude factor that goes like this with frequency and a phase, so an oscillating signal with a phase that traces the orbital phase of the binary. So you can expand this phase in terms of the orbital velocity that you can use as a small parameter, especially when you're early in the INSPIRAL, so that this parameter is much smaller than the speed of light. And you can end up with what we call the post-Newtonian expansion of the phase. And these coefficients of this post-Newtonian expansion, they are basically calculated within the given theory, so within GR, to have a certain functional dependence on the parameters of the binary. So the masses and the spins of the binary, of the black holes. Of course, as you go closer to the merger, this perturbative expansion breaks down, and you have to kind of complete the picture with numerical relativity simulations that they use the full Einstein equations instead of just a linearized version or a perturbative version, post-Newtonian version. So this expansion has been calculated up to a higher order, so n equals 7 or n equals 8. So regarding the inverse problem, you have a large parameter space to sample. So the parameter space for a typical compact binary coalescence would be made of mass 1, mass 2, spin 1, spin 2, so eight intrinsic parameters already. And then you have extrinsic parameters, so the distance to the source, the sky location angles, the inclination and polarization angle, the time of coalescence, and the phase at coalescence. So it's a high-dimensional problem, but there are still efficient algorithms like nested sampling that we can use to calculate the evidence, which is this purple bit right here, the probability that you see the data given a source of specific parameters, theta, and your background hypothesis, etc. And from this, you can, using Bayes' theorem, you can calculate the posterior probability distribution on your parameter space. So what is the probability that the source is described by the parameters theta, given the data that you observe and your background hypothesis, like typically a GR underlying theory, or possibly some alternative, and other assumptions that you make on the way. I will not spend more time on this. I will go to results basically, because there's plenty of results that I need to go through. So I think I will try to be as quick as I can, and just basically try to convey the essence of the results and not go into great detail. You can ask more information if you are interested in a particular test or a particular result. So I will split the test into 3 categories or 4. But the basic idea is that you have the source, you have the gravitational wave generation in the source. So yeah, 3 categories. Then so the life of a gravitational wave starts at the source where it's generated. You need to know your theory very well to model it there. Then it goes through a very long propagation period. So the first gravitational wave, for example, that we observed, it was traveling for about 1/10 of the lifetime of the universe, which is quite amazing if you think about it. So propagation may play an important role, and it may give you significant evidence for understanding the underlying theory. And finally, it reaches our detectors and gets projected on our output stream and is presented to us as raw detector data. So that is a third part that gives us some additional information. So before we go into those tests, into those categories, there's already a 0th order test that one can make with gravitational wave data. So if you have a model and you have your data, you take your best fit model waveform across the entire parameter space, the best fit, and you subtract it from the data. And what remains, you expect it to be made of pure noise. And since you know what your noise looks like, the stochastic properties of your noise, you can ask the question, is that picture consistent with the residual data stream being made of pure noise? So we did this for the first detection. So by the way, in the following slides, typically I will give you the first result that we got from the first detection, GW150914, and then the latest update with the entire catalog of detections that we have published so far. So, for example, with the first detection, we subtracted the best fit waveform from the data, and we asked the question, is the residual signal power or signal energy, is it consistent with what you would get with pure noise? And then you construct what you call the noise background. So you analyze stretches of data where you know that there is only pure noise. You believe there's only pure noise, so no significant signal in there. And you see what kind of signal to noise ratio, so what kind of energy resides in this signal. And then you plot the value that you get from this particular measurement, where you got the time series of around the time of detection, and you subtracted the actual your actual model. So we see that the residual SNR, as we call it, the residual signal to noise ratio, is well within the bulk of the background distribution. So with good confidence, it's consistent with there not being any residual signal after we subtract our GR waveform. So this is a first order, a zeroth order test, as I would call it. We did the same for all the sources in the latest catalog, so the 50 odd sources that we had during the last 5 years, and we plotted the distribution of those residual signal to noise ratios, and you can see the p-value. So you can basically calculate the p-value by going here and looking at the cumulative distribution function and reading of this number. So 1 minus this number is basically what you would call a p-value, typically, roughly speaking. So overall, there seems to be no significant evidence, no evidence for any residual in the signals. You can also do what we call a meta p-value test. So you can statistically, if all these signals were consistent with noise, or the residual were consistent with noise, you would expect the p-value to be evenly distributed, uniformly distributed between 0 and 1. And this is what you see in this, what we call the PP plot. So, if your p-value is what you would expect to see if everything was just noise, it would be on the diagonal. So within the statistical uncertainties, these p-values are consistent with the diagonal, basically. Next, we go to gravitational wave generation, which is quite a bit more tricky, because you need to kind of parameterize a model of GR violations, basically. So let's see what we did for the first detection. So if you remember, when I described the Poissonian expansion as a perturbative expansion in the phase with these phase coefficients, etc. A typical modification of the underlying theory of gravity would predict modifications in those post-Newtonian coefficients. So you would expect this psi or phi coefficients of the expansion to vary with respect to the GR predicted value. So what we can do is we can extend our model, add an additional free parameter to it, like the 0th order or 0.5 or first order post-Newtonian phase coefficients, and modify them, like shift them, allow them to be modified, to be away from the GR predicted value, and then we can use those as an additional free parameter in our parameter space, and try to measure them together with all the other parameters and see what the posteriors give us. So what the measurement give us. And we define this parameterization of GR violations in this way. So we take a post-Newtonian coefficient and we vary it by a relative shift delta phi I, where I denotes the post-Newtonian order. And then we plot the to summarize, we didn't see any violation of GR. So 0 was always within the bulk of the posterior, and we can just plot in this orange squares. We can plot the upper bounds that we got from this measurement, and those upper bounds, they basically gave us for the first time constraints on high post-Newtonian orders or the coefficients that we they are only accessible in highly relativistic systems. We also calculated the odds ratio between the hypothesis that the underlying theory is GR, or the underlying theory is a modified theory with a modified post-Newtonian coefficient. In all those cases, the hypothesis test favored GR over any modified alternative. So this is an interesting plot because, for instance, the GR dynamics are encoded in these post-Newtonian coefficients. And for example, nonlinear tail effects that correspond to, for instance, gravitational waves scattering off the Kerr-like background of the binary and contributing to the observed signal, they come in at 1.5 post-Newtonian order, so they correspond to this variable onwards. Spin orbital couplings are also encoded in this variable. Spin-spin couplings of the binary are encoded in this variable. So, you know, you can start probing different aspects of gravitational wave geometry dynamics, compact binary geometry dynamics by measuring these numbers, these quantities. Here I'm listing separate. So I give separate attention to results from the first neutron-star binary coalescence that was observed in 2017, because typically they can give different, either improved or different set of measurements. So in this case, because this is a low mass binary, it entered the LIGO-Virgo sensitivity band much earlier, so many thousands of cycles before merger. We have access to many INSPIRAL cycles, and so we probe smaller values of V by C as well. So this, you know, you get a boost in your measurement at low post-Newtonian order, and you start becoming competitive with pulsar binaries at, you know, in these low post-Newtonian order measurements. And this is the set of results from the recent catalog. You can see, you know, in each of these colored short horizontal lines correspond to an event from a black hole binary. There is also the blue points that correspond to the neutron-star binary merger, and the red dots are they correspond to the first catalog results, so that we compare, you know, the improvement on those constraints. And you can see, you know, at low post-Newtonian order, we are getting an improvement. So we're starting to probe 10⁻². And at high post-Newtonian order, so across the entire spectrum of results, we're getting improvements by stacking more and more sources together. And this is what the posterior distributions look like. So the different colors correspond to different waveform models, but overall they agree with each other. I will try to rush through this, so I will not spend much time on the BNS, but I would like to point out that, you know, there is a new type of test that became available once we observed GW170817, so the neutron-star binary merger with both gravitational waves and with electromagnetic observations, because we could then fix the location of the binary in the sky, and we also observed light emission, you know, in time coincidence with the end of the INSPIRAL, so with the merger. So by comparing the arrival times of gravitational waves and electromagnetic radiation, we basically are able now to compare the speed of gravity versus the speed of light. So this is a really interesting result that can exclude many theories, alternative theories of gravity that predict gravitational waves traveling at speeds that are significantly different than the speed of light. Because now we have a bound because of the long distance that was traveled by both signals and the very good coincidence, we have a bound of this differential speed of the order of 1 part in 10 to the 15, which is quite impressive. And a similar thing you can say about the equivalence principle. So you know that gravitational waves and light, they both travel on the same kind of geodesics, and they undergo the same Shapiro time delay to this extent. And you can use this to project these constraints on constraints of parameters of any alternative theory you may think of that predicts otherwise. A side result regarding these post-Newtonian measurements is the following. So remember when we said that black holes are very simple objects, and they once you know their mass and spin, you basically know all the properties. This is known from the so-called no-hair theorem or two-hair theorem for Kerr black holes. So there are only two numbers that you need to know about a black hole, and then you can infer everything else, including, for example, the spin-induced mass quadrupole. So this is a mass quadrupole that contributes, as a quadrupole, it contributes to the gravitational wave emission and the waveform that you observe. And this is, so this coefficient here for black holes, it has a value of 1. If you had a neutron star or something else more exotic, like a boson star, or, I don't know, a quark star, or a black hole with some hair, with some sort of scalar hair or vector, or Procast star, or whatever, you would get a different value for this number, and you would see it as an additional modification of the phase of the gravitational wave phase at second post-Newtonian order. So this is one of the coefficients that we can test, and we can see that within our uncertainties of measurement, our measurement uncertainties, this mass quadrupole coefficient is consistent with what you get for a Kerr black hole. So you basically probe the nature, the Kerrness of the black holes. This is, by the way, this is a combination of the two kappas for the two component black holes. This is the symmetric kappa. So you know, because they both contribute to the same, with the same post-Newtonian order in a single term. So you cannot distinguish between the two. But yeah, this is already an interesting result. Next, we go to gravitational wave propagation. So like I said, since the generation of gravitational waves, they have traveled a long distance, and many things can go different in different theories of gravity with respect to gravitational wave propagation. So the gravitational wave may not propagate at the speed of light, for example, if a theory predicts a massive graviton. So, you know, could there be and there are theories, proposed theories of massive gravity. Theoretically, there had been problems in the past that were successfully solved in the recent years. So there are still viable theories that predict a massive graviton. So the question is, do gravitational waves propagate at the speed of light? And in GR, the answer is yes. If you think of the linearized kind of field theoretical picture of gravitational waves as a spin-2 field, so you can think of gravitons in a kind of loose sense of the word, without even having a full theory of quantum gravity, of course. You would say that if you could have a gravitational wave dispersion relation or a graviton dispersion relation with a mass term, and you would associate either a mass parameter or a Compton wavelength parameter to this mass term of your dispersion relation. And then your gravitons would, or your gravitational waves would not propagate at the speed of light and would not propagate at the same speed for different frequencies. So you would have dispersion, as we call it. So massive graviton would cause dispersion. So this is what a massive gravity, the dispersion relation for a massive graviton would look like. You would have an additional mass term here, and this is the Compton wavelength corresponding to this mass. Then you would have a group velocity for the waves that is dependent on the energy. So you would have a frequency-dependent speed of gravitational waves, which means that higher frequency waves would travel faster than low frequency waves. And if you think about if you think of the gravitational waveform that comes from a compact binary, which has like a chirp form, it's increasing in frequency and amplitude until merger. So, low frequencies get emitted earlier, high frequencies get emitted faster. And if higher frequencies travel faster than lower frequencies, then this would lead to higher frequencies catching up more or less. So this would lead to the gravitational waveform getting kind of squeezed in time. And this leads to I mean, you can follow the calculations in this nice paper by Clifford Will, and this leads to a nice frequency domain modification of the phase that shows up as like a one Poissonian order effect. And this is kind of an animation that shows how a waveform gets modified if you add dispersion. And you can see how the waveform gets squeezed together as you increase the mass of the graviton. Or you decrease the Compton wavelength from infinity to finite values. A generalization of this is a modified dispersion relation with an arbitrary additional term here, with an arbitrary power of the momentum to some power exponent alpha. For alpha equals 0, you get massive graviton. For other values, you typically get Lorentz invariance relation. So you can map these to, these kind of effects occur in theories like doubly special relativity or Hochschild-Lifshitz gravity, and you can kind of map these values to alternative theories, or at least leading order. And again, we have a nice closed form for the modification of the phase of the gravitational wave phase in the frequency domain. So by adding this modification in our waveform model and leaving either the graviton mass or graviton Compton wavelength, or this this length scale that defines this term here as an additional free parameter of our model, we can try to measure it together with the other parameters of the binaries and constrain this effect. And this is what we did. So this is from the first event. We constrained the mass of the graviton to be less than 1.2 times 10 to the minus 22 electron volts. So the measurement was essentially consistent with the mass of the graviton being 0. And this is the upper bound at 90% confidence. Then, improvements came when we added more and more sources. We also constrained the different, so for the different values of alpha here, you get you can constrain the amplitude of the additional term, the magnitude of the additional term like this. And similar in a similar fashion, you add it as a free parameter, and you test the different hypotheses for different values of alpha, and you put your constraints on this additional parameter. Yeah, and since this is a number that is universal across all the different sources, you can more or less stack the results, the posteriors, the results from each individual event into a total overall number for a catalog. These are the results for the first catalog with the 10 sources and the second catalog with all the 50 sources that we released recently. So if you have a favorite theory that predicts a modified dispersion relation, you can look up the modification. You can, if you're lucky, it will correspond to one of these values of alpha, and you can read off the bound here and translate it into a bound on your modified theory of gravity. So different positive and negative bounds on this parameter correspond to subluminal and superluminal bounds. And you can see here what the posterior distributions look like for these additional parameters. Yeah, and this is just the catalog of the current results. So the current bound of the mass of the graviton and all the other different terms in the modified dispersion relation. I will skip this, I think. Basically, let me just give a very brief summary. Since you have a neutron star binary merger that you observed electromagnetically, and you have an independent measurement of the distance to the source by electromagnetic observations, you can also test. You can also see if gravitational wave amplitude has leaked into extra dimensions. So you would have a different scaling of the amplitude if you had gravitational waves leaking into extra dimensions. So you can constrain theories of higher dimensions in principle. Finally, some tests on the final remnant black hole. One of the tests is what we call the INSPIRAL MERGER-RINGDOWN consistency test. You basically split the waveform. So you have basically, your binary goes under different stages. You have the very long INSPIRAL, you have a merger, and you have the final black hole, which acts as a highly perturbed Kerr black hole, and very quickly radiates away this asymmetry and ends up in a quiescent Kerr state very quickly. This is what we call the ring down. So if you split your waveform model into the early INSPIRAL and the post-INSPIRAL part of the signal, you can try to measure with the early INSPIRAL, you can measure the progenitor masses and spins of the two black holes. With the post-INSPIRAL signal, you can measure the final black hole mass and spin. And GR, or rather results from numerical relativity, gives you a mapping, a relation that maps the progenitor masses and spins to final mass and spin. So there are accurate empirical formulas from numerical relativity simulations that give you this relation. So you can see if these two different individual measurements give you consistency in the final mass and final spin of the final black hole. And with the first detection, this is what we did. The INSPIRAL gives you a posterior, 90% posterior contour over here in the mass spin plane of the final black hole. The post-INSPIRAL gives you a singular region that overlaps in this region with the INSPIRAL signal. And if you do the full INSPIRAL MERGER-RINGDOWN analysis, it kind of overlaps with the overlapping region. So that kind of gives you consistency, and you can see this as a plot, a posterior plot on the delta M and delta A of, so delta mass and delta spin of the final black hole, which should be consistent with 0, which is the GR. So that passes the test. We also do this with all the events from the catalog that have significant contribution to both the INSPIRAL and the post-INSPIRAL part of the signal. And we see that in most cases, this, the GR value of 0 is well within the posterior distribution. There are a couple of cases where that is not the case. So these 90% contours are outside the 0. So GR is outside this the measurement. But in both those cases, these are cases where you have a very low signal to noise ratio in the post-INSPIRAL part of the waveform. So there's really quite a lot of uncertainty in the post-INSPIRAL waveform. And the fact that, an additional thing to note is that these sources are, I think both of them are have high mass ratios, so you need higher order modes to get a good model. So it could be an effect of model systematics. It can very easily be an effect of waveform systematics together with a very low signal to noise ratio in the merger and ring down, so high frequency part of the signal that gives you this inconsistency. But it's interesting nonetheless. Right. So finally, if I have a couple of minutes, I will talk about the ring down and the test of the kernels of the final black hole. So like I said,
perhaps very briefly though, because we are running out of time.
yes. Okay. So I'll just repeat that to know all the properties of the final black hole and its eigenmodes, let's say, in which it rings. You just need to know its mass and spin. So if you can measure the frequencies and damping times of the so-called quasi-normal modes of the final black hole, which are kind of the resonant modes, let's say, of the final object, then you can perform consistency tests if you can measure more than 2 parameters out of this set. And we have shown that we can do this, and and in the catalog there were a couple of events for which we could actually make a meaningful measurement of this. Still, it's very high uncertainty, but the general idea is that the result is again consistent with what GR predicts. So it's consistent with the final object being a Kerr black hole. But again, there are quite large uncertainties. But with future improved instruments, with higher signal-to-noise ratios for high-mass black hole binaries, we will be able to probe further. Finally, we check whether there is anything even after the ring down, and this is motivated by the so-called exotic compact objects, where you have a very compact object that just instead of having a horizon, it has a very thin structure that replaces the horizon. So basically, you can think of it as a potential barrier problem, where instead of having only ingoing modes at the horizon, you may have a feature like this, a structure replacing the horizon, where you have trapped modes that periodically leak out towards infinity. And this will give you a set of repeated echo signals, like after the black hole has devoured an inspiraling object, it will basically burp out a series of bursts of gravitational wave radiation. So we check whether there's anything after the end of the ring down that resembles a repeated burst signal, like echoes. And we have found no evidence. So this has been motivated also by people who have claimed to have seen things like this in earlier events. But in general, if you do this properly, either with a modeled analysis, so a template-based analysis with a particular model, or a model-independent analysis, you will find that this hypothesis is not favored. So the INSPIRAL MERGER-RINGDOWN echo hypothesis is disfavored with respect to the INSPIRAL MERGER-RINGDOWN without echoes hypothesis. Of course, it's important how you formulate that hypothesis, but yeah, that's in any way we have seen it so far. We have done it so far. We haven't seen any evidence for the existence of echoes. Finally, for a few seconds, I will just point out that in GR you have two polarizations: the polaris and cross polarization. If you have a scalar or a vector field, you can have non-transverse or non-traceless polarizations along the direction of propagation, for example, or this is a breathing mode that you see when you have scalar fields. And you can test whether you see these in your detectors by, again, by modeling your hypothesis correspondingly and looking at the joint data, coherent data projected on each of your detectors. So you can only do this with a multi-detector network in order to resolve the degeneracies between the different polarizations. And so far we have seen no evidence for the existence of any signal that has a non-tensorial nature, so in terms of polarizations. So this was a very quick kind of overview of this result. And there are, of course, many more interesting things that you can do with gravitational waves. Unfortunately, I could not go through all of these interesting considerations here, but this is a kind of a relatively short list of those. The test of the area theorem, blah, blah, blah. And you can also try to convince your theoretician friends to give you accurate predictions for things like, the quasi-normal mode spectrum of black holes in modified theories, or the modification of in-spiral dynamics of alternative theories of gravity, etc. And you can also try to convince your numerical relativity experts, friends, to perform numerical simulations with those alternative theories. So you have something to do apples comparisons against GR. So this is it. And I would like, apologize for going over time. And I would like to leave you with my conclusions. So, to conclude, gravitational waves are great. We have plenty of those, especially in the recent year, in the last year. So far, general relativity is alive and kicking. We have probed it with many different ways using gravitational waves so far. You can also play with the data and then the results. You can find the raw data from the detectors in this website, gravitationalwaveopenscience.org. And you can also find the posterior samples from our test of GR analysis in this website. So yes, I would like to leave you with this. Much to look forward in the future, and of course with future detectors even more. So thank you very much again for your attention.
Thank you very much, Michali. We have a little bit of time for a few very brief questions and very brief answers. So please feel free to just turn on your mic and ask if you have any questions. Vasily?
Ευχαριστούμε, Michali. This was a very interesting talk. I have a question actually which may be similar to what Nikos Serioulas actually also has raised. Right now you have enough supermassive black holes to do some statistics, right? As a result, enough black holes from black-hole merger to do some sort of like statistics in terms of the mass function, right? So the question is that if you have, if the black holes, the stellar mass black holes are the outcome of core collapse supernovae mostly, right? Or possibly neutron star mergers. Can you say something about what the theory, can you compare the results that you have in terms of the masses that you found with what the theory, say from core collapse supernovae, was telling us, in particular about the fact that there is a gap where you cannot create black holes just because when the collapse creates pair instabilities and you have sort of like complete annihilation of the core.
Yes, I can, even though this is I think I can answer this. If I go to the early slides with the masses here, yeah, we can see that there are the mass populate region that is supposed to be forbidden if you consider pair instabilities. But whether that is because of, so the most real answer to this is that such black holes can be formed, as second generation. Such black hole mergers can be the second generation mergers. So this forbidden black hole could have been formed in a dense environment, like in a cluster, from two later black holes that coalesced earlier on. The alternative, you can say your theory may be wrong and there may be not such a pair instability, and this may be attributed to either a modification in the theory of gravity, in the underlying theory of gravity, or some other dynamical feature that has been taken into account for the core collapse mechanisms. I think there are uncertainties for the bound, for the gap, are still quite significant. Maybe not significant enough to cover the entire gap, but I think this is like, it's a multifaceted problem, and I don't think there is a definite answer to this, but definitely the most likely scenario is that black holes in this forbidden range may have formed as during earlier mergers of lighter black holes.
Thank you.
We have another question. Please go ahead and ask. Panayoti.
Yeah, thanks for your nice talk. So in gravitational wave analysis, we compare basically observed waveforms to numerical relativity waveforms. And I think there is some recent work that discusses that maybe what we compare to actually the numerical relativity waveforms may not be accurate enough. So I was wondering if you have any thoughts or are maybe other approaches discussed in the community or workarounds for this?
Yeah, so we're not at the point yet where this is a really pressing issue. So the problem is the competition between measurement uncertainties, so statistical uncertainties, and waveform systematics. So we're not at the point where the waveform systematics would dominate our measurements. So in other words, if our signals start becoming loud enough so that discrepancies in our waveform models become important for, and lead to biases that are greater than our statistical uncertainty, then yeah, we need to work on the waveform models much more. And this even though we're not facing such a problem right now, it's approaching very quickly. So within the next few years, we will, the sensitivities will improve, the closest sources, so the loudest sources, will become much louder. And eventually, when we compile information from different events, we will lead ourselves to biased results. So this is something that people in the NR, in the numerical relativity group within LIGO, but also outside LIGO, numerical relativists are working on improving, numerical relativity waveforms accuracy, and also the models that get information from numerical relativity and encode them in a hybridized waveform, let's say. Because of course you cannot do your data analysis with numerical relativity waveforms, because these are extremely expensive. You just need to to find the balance between analytical approaches and results for the late INSPIRAL and merger from numerical relativity. So as long as both of these efforts improve over the next few years, I think we will be safe until next generation gravitational wave detectors. But this is a fair point. In next generation gravitational wave detectors like Einstein telescopes, Cosmic Explorer, and even worse, LISA, we will have quite a lot of work on our hands from the modeling perspective.
Okay, any other pressing questions? Okay, if not, non-pressing questions will have to wait until the first opportunity when the pandemic goes away, when we have Michalis visit us here in person, which we would very much like. Thank you very much again, Michalis, for this very interesting talk, and thank you all for joining us. See you next week. Bye-bye. Thank you.